Our third video on motion will cover uniformly accelerated motion. Uniformly accelerated motion is when acceleration of an object is constant. Some examples of uniformly accelerated motion would be a ball rolling down a straight incline, an object being dropped from a building, or a car increasing its speed at a constant rate. When we solve problems involving uniformly accelerated motion, we will have to choose between one of these 6 formulas. Let's take a quick look at all 6 formulas. First, we have V average, or average velocity, is equal to final velocity plus initial velocity divided by 2. Acceleration A is equal to final velocity minus initial velocity divided by t, or time. Final velocity is equal to initial velocity plus acceleration times time. Displacement is equal to initial velocity times time plus 1/2 acceleration times time squared. Displacement is equal to 1/2 the quantity final velocity plus initial velocity times t. And 2 times acceleration times displacement is equal to final velocity squared minus initial velocity squared. Depending on which variables we know and what we are trying to find, we will need to pick a formula that only includes what we are given and what we are trying to find, nothing else. Let's take a look at an example of uniformly accelerated motion. A car starting from rest reaches a final velocity of 297 kilometers per hour. Find its average velocity. The very first thing we want to do with all of these problems is write down the information we are given. We know that the car is starting from rest, so the initial velocity is 0. The final velocity, we are told, is 297 kilometers per hour, and we are trying to find the average velocity, or V average. Out of the 6 formulas we just looked at, only one includes only initial velocity, final velocity, and average velocity. That equation is V average equals V sub f plus V sub I divided by 2. Since this problem is written in terms of average velocity, we don't need to rearrange anything to solve, so our basic equation is also our working equation. Next, we can substitute the data we are given, so V average equals 297 kilometers per hour plus 0 kilometers per hour divided by 2. Make sure you use parentheses in your calculator when you are adding in the numerator. When we solve, we see that the average velocity is 149 kilometers per hour. Let's take a look at one more example of the accelerated motion equations. A train slowing to a stop has an average acceleration of negative 2.75 meters per second squared. If its initial velocity is 25 meters per second, how far does it travel in 6 seconds? First, let's write down all of the information we are given. We know that the acceleration is negative 2.75 meters per second squared. Since it is negative, it just means that the train is slowing down. The initial velocity is 25 meters per second, and the time is 6 seconds. We are trying to find how far it travels, or the displacement s. Out of the 6 equations we looked at a few minutes ago, there's only one that includes acceleration, initial velocity, time, and distance. The rest of the equations include final velocity. In this case, we don't know what final velocity is, nor are we trying to solve for it. That means the only equation that we can possibly use in this problem is s equals vit plus 1/2 at squared. Since this equation is written in terms of displacement s, the basic equation is also our working equation. Since we don't have to rearrange the basic equation, we can go right to the substitution. This gives us s equals 25 meters per second times 6 seconds plus 1/2 negative 2.75 meters per second squared times 6 seconds squared. We will follow the order of operations and perform all multiplication first. Using 3 significant digits, this gives us 150 meters minus 49.5 meters. We are left with units of meters because meters per second times seconds leaves us with meters, and meters per second squared times seconds squared also leaves us with meters. Subtracting and then rounding to the nearest whole number, because our least precise number, 150, is only precise to the nearest whole number, our answer is 101 meters. This concludes our examples of the accelerated motion formulas.